Hello everyone, welcome back to another GIS statistics lecture video. And in this lecture video, what I want to talk about is this idea of AIC and dredging. AIC and dredging. Right, and so what dredging basically does, start with dredging. What dredging basically does, and we're going to look at examples of this in R, is dredging basically takes whatever variables you think you want to use, and it creates every possible subset of those variables. Right? So basically what it does is it creates submodels which use every possible combination of variables. And compares them. So basically you feed it in the things you think are important, it breaks that apart and compares every possible combination to guarantee, or I shouldn't say guarantee, but to give you some statistical measure of whether or not the variables, the combination of variables you have are the best model you could make. Or maybe there's a case to be made for using fewer. As a general rule, you will typically find that if you follow the guidelines that we've proposed previously, where you think about the relationships before you model, where you look at the relationships in terms of scatter plots and correlation, and you make what we'll call the global model, which is everything you think matters, and then you look at the p-values and the coefficients. If you do all of that first, typically dredging is just going to confirm what you think, right? It's generally not going to overturn any of what you've thought. It might, but generally if you've done your homework in advance, dredging is just another line of evidence saying that, hey, we have the best set of variables that we could have. So how does dredging actually compare them? Right? How does dredging do this comparison? Well, it does this comparison with something called the AIC information criteria. AIC information criteria, or AIC. And what I want to do is I want to talk about this AIC for a second. So let's go ahead and walk through what AIC is trying to do conceptually, walk through the equation, and walk through how we interpret it. So just to sort of recap what I just said, right? AIC, or the AIC information criteria, right? This is a measure of model performance that quickly allows you to compare models. Now, unlike things like p-values and r-squareds, right, this is unbounded, which means that it can be any real number. Right, AIC can be any real number. And so to understand sort of what the, to sort of interpret AIC, we need to know a little bit about the data. And in order to explain what we need to know, I think it's best to jump right into how AIC is calculated and how that calculation relates to a data set. Okay? So, AIC in general is equal to n times the natural log of SSE. This is sum of square error, which we've talked about before, but I'll recap in just a second, over n plus 2k. Right, so this equation hopefully doesn't look that intimidating. That's because it's really not. Right, this n right here, right, this is the number of samples. Right, so if you're doing a regression where you're looking at counties, right, n would be the number of counties. If you're doing a regression that's looking at the number of people, right, n would be the number of people. If you're doing a regression that was looking at some sort of, the thing you were actually studying was an animal, right, n might be the number of individual organisms that you have. So again, right, n is just the number of samples. K over here, right, this k, right, this is the number of variables. Or I should say the number of independent variables. Right, and so if you were doing something where you were trying to model the poverty rate in a county, and you included median income, percentage of African Americans, and percentage of people with bachelor's degrees, where you'd have 3 independent variables. So your k in that case would be 3. Right. So again, n is the number of samples, k is the number of independent variables that you have, and then this this SSE here, this is the sum of square error. And so just to quickly recap what the sum of square error is, right, the sum of square error is just the summation from I equals 1 to n of y minus y hat squared, right? Where again, right, n is the number of samples, right? This is the actual value, and y hat here is the predicted value. So, a couple properties of AIC. Let me scroll down a little bit. Right, now that we sort of understand where AIC is coming from, right, we see that it includes this error term here. Right, so again, the closer these two are, right, the closer y is to y hat, right, the smaller this number is. Hopefully everybody sees that and understands that, right? And so because of this property, right, because this thing here is going into this thing here, we're also dividing by n, right? So basically, the lower the AIC, the better. The lower the AIC, the better. Now, the reason I said it's unbounded and it can be any real number, right, is because again, depending on, you know, what your actual value was for your or what the range of values was for your y, right? This sum of square could be any number, right? If y goes from 0 to 1, right, this is going to be pretty small. If y goes from, 1,000,000 to 0, right, this number could be really, really big. Again, the number of samples you have, right? The more samples you have, right, that's going to change this number. Also, the number of variables you have is also going to change this number. So again, right, any real number, because you can have different numbers of samples, you can have different numbers of variables, and the range of your dependent variable is going to impact what this sum of square error number can be, or what range would make sense for this sum of square error number. So, that being said, AIC really works best when comparing models that are subsets of each other. Let me scroll down here. AIC works best when comparing models that are subsets of each other. Right, so put another way, AIC works best when the only thing we're changing in this equation is k. Right, we're not changing the range because we have the same dependent variable, so we're not changing the range that the SSE would make sense over. Right, we're not comparing one model that has, y values going from 0 to 1 and one where they're going from 0 to 1,000,000, right, because that would completely obliterate AIC. So our standard square, or our sum of square error here is going to be within the same range, right? Our n isn't going to change. The only thing we're changing here is k. So that is the principle behind using AIC for comparing models. And again, best when they're subsets of each other, which again, this subsets keyword, right? If we scroll back up here, that's the whole point of dredging, right? We're creating submodels. We're comparing different sets of variables to each other. So hopefully this makes sense. Hopefully this idea of AIC makes sense. Again, to reiterate, right, the lower the AIC value, the better. And AIC, again, works best in the case what we're using with dredging of having models that are essentially subsets of each other. So hopefully this makes sense. And as always, please reach out. Thank you.